All right. So now we are going to start looking at the basic ideas of aerodynamics, okay, very basic ideas. So those of you who are coming from non-mechanics background, like not from, so you may have to just recall these ideas, okay, which would be required to understand. So the basic physical quantities of a flowing gas, like idea about pressure, density, temperature, flow velocity. So what is pressure? Pressure is your, if I take any body or any object and apply some force, uniform force over a surface, the force applied divided by area is your pressure typically, and it can be defined as a limiting quantity as limit of dF by dA, where you have dF is your infinitesimal force and dA is your infinitesimal area. Yeah. So, as dA tends to 0. Density, yes, it is a very important parameter because this is one of the key things which affects your UAV performance dramatically. So, whatever UAV actually does at sea level, where you have usual assumed density of air, that we will typically take at 1.225 kilograms per meter cube. So, this is your standard density. Now, once I go to higher altitudes, this density starts to drop, and this could actually directly affect our aerial vehicle performance in a big way, and how it does that actually we will see. So, one simple thing is of course, that as we will see the lift force acting on a aerial vehicle is directly proportional to this density. So, if my density drops, my lift force for the same speed will also come down, which means my fixed wing UAV would actually have to fly faster to generate same amount of lift with a reduced density. So, that is one way. If I look at quadcopters or multicopters, so your propeller which is spinning at a certain speed and it is generating enough lift to support your entire quad rotor weight. Now, when I go to higher altitude, my density drops down, which means now my propellers would have to spin at higher RPMs, which means if a normal quad rotor, so normally if you have built or flown quad rotors, we talk of throttle percentage. At what throttle level? I mean, it becomes airborne. Normally, we as a designer, we try to set it as 50 to 60%. 50% is optimal, 60% is what you can still tolerate. So now, if it is taking off at 50 to 60% throttle at sea level, the moment I take it to Leh Ladakh or Tawang or somewhere, I mean at 3000, 4000, 5000 meters above mean sea level, my density will drop so much that my throttle would actually go to levels as high as 80-85%. Okay. So, same quadcopter with no change, it will now take off at almost 80-85% throttle, which actually is quite challenging. Why? That is secondary. Yes, that also will affect. Sorry? No, thinner air is causing this, but question is what exactly, how would this impact my quadcopter's behavior?
Might stall because if it's reached 100.
Right. So, no, the stall is not the correct term here for a quad rotor, because quad rotor does not stall, but what happens is that, I mean, if you are already at 80%, to maneuver a quadcopter in if I want to fly it forward, backwards or whatever, or there is gust of wind something coming, to counter all that I would require the RPM to increase. So, if it is going beyond 90%, then you are already at a point where, I mean, my motor is at max RPM, it will consume tremendous power, it may even sort of saturate, not stall, saturate. So, my control bandwidth is severely compromised and invariably my quadcopter can crash. So, this is the most novice mistake which lot of new startups do, especially people who are coming purely from integration background. Nothing against electrical and computer science engineers, but I mean people who are coming from that background, they have no idea, okay, what this density fellow does to us, and they happily make a quadcopter, oh, this can do this and that, and then they go to Ladakh and khadak, it goes down, it goes in, it falls in some this crevice or whatever, I mean. So, that is the fate of lot of designers actually, especially people who are not really designers, they are integrators. They just look at things on internet and they suddenly think, I mean, that they are a UAV designer, right. So, there is a big news recently regarding this 20-year-old kids, I mean, building technology or this fast moving drones for defense requirements, right. But yeah, I mean, everybody knows that, I mean, that is something which you can look up on internet and make it yourself. So, it is no big deal about them. And now they have been so overhyped that they will now expect that, I mean, they can design and build anything, which it does not work like that at all. Even after having worked in this space, UAV space for almost 15 years after coming to India, and before that I mean almost 10 odd years or 6 odd years, I mean I have been observing other people, I mean working in this domain and learning from them. Even then it is not an easy thing at all. Okay. There are so many things which you have to rigorously look at, okay, and which we will try to highlight as we go through this course. Okay. Right. So, density. So all this story is about, I mean, how important your density as a factor is. Okay. Temperature. Yeah. So, your density gets affected by temperature. Although, I mean, sometimes you may end up using your ideal gas equations, it need not, I mean, always work like that. Also, we talk about, so at one point I will define you the International Standard Atmosphere. What is that? So, that is actually basically a table which tells you that how my temperature, pressure, density is at a particular altitude and how does it vary with different heights. Right. So, you will be able to know without actually having to go to Leh Ladakh and actually measuring density there or trying to find it out, I can know, but then this is ideal atmosphere, okay, and real atmosphere is not exactly identical. So, in India we talk of Indian reference atmosphere, which is slightly modified version of your international standard atmosphere. How so? India is actually a warmer country. So, you would be amazed to hear that when say HAL designs a large manned aircraft, I mean a helicopter or airplane or anything, they talk about testing it in hot and dry conditions. So, that is Rajasthan. They talk about testing it in hot and high conditions. So, you will say what is hot and high, right. So, high we understand, I mean we will go to Leh Ladakh, I mean Siachen, right. Siachen is a fairly cold place. So, why hot and high? Hot compared to your international standard atmosphere. So, in India we often take 15 degrees plus as Indian reference atmosphere, which means, I mean your tables would have to be modified slightly. So, whatever your international standard atmosphere tells you, I will modify it slightly and my density will be even lower compared to what my ISS says, because the temperatures are actually higher. Okay. So, anyway, once we talk about that, we will go into more details of related to my international standard atmosphere. Flow velocity. So, flow velocity is the speed at which my gas is flowing, and I can take any fixed point and look at an infinitesimal fluid element as it sweeps through that particular fixed point, and that becomes my local velocity. And overall, I mean for a nice steady flow, we assume same velocity everywhere. So, in all our studies calculations, we will assume free stream velocity to be one uniform velocity. Okay. But in real world, that is not how it happens all the time. Okay. You will have turbulence, perturbations and so on and so forth, but we cannot model that at this level right now. So, now we will also do some more definitions. So, we looked at the cross section of the wing in the previous class, and we said that, I mean it has a peculiar shape which is called a streamlined shape, as opposed to something which is not streamlined and bluff, such as, I mean like rectangular objects, flat plates, or if I look at cylindrical objects. So, these are all bluff bodies. Okay. So, the flow over them are not very nice. Okay. They would actually separate out quickly and create a lot of drag. So, in design of UAVs, we would ideally want to avoid any kind of bluff body shapes as much as possible. Sometimes it is not really possible, but as long as we can, we will try to put some elliptical shapes or more narrow streamlined bodies. So, my drag is lower. So, now if we put an airfoil into a flow, okay, so you have a nice continuous flow, and we observe the path that the fluid particles take around the object, and if you trace those paths, that path actually ends up becoming a streamline. So, path taken by a moving fluid element is called a streamline. So, you would wonder, okay, I mean I do not see any streamlines, right here. How do I visualize that? So, to do that, because my air is transparent, I cannot see that. If I inject some amount of smoke or some other colored particles, then one can actually start seeing these things, and I will show you the video next slide, which will exactly give you how this really looks like. So, what happens now? I mean if I stuck this airfoil and there is flow over them, so which has a peculiar nature. We can see that on the top surface the flow is getting sort of bent and goes over the airfoil. Also the airfoil you see on the top surface, okay, sorry here. So, this shape, right, okay, so this shape that you are seeing here versus this particular shape or this particular shape, do you see any difference?
There is a difference in the camber.
Yes, exactly. So, what is that? So, you see the top surface and the bottom surface in this particular airfoil are identical, right. So, it is a symmetric airfoil. I can easily draw a line connecting the. So, this point is called the leading edge, and this end point is called the trailing edge. Right. So, if I connect these 2 points, that particular line is called the chord line. So, for a symmetric airfoil, we see that the both surface, the top and the bottom is identical. So, if I flip it over, it does not make any difference to me, it is the same thing. Okay. But if you look at this other airfoil, it actually has a peculiar curved shape. So, I can maybe draw some, right. So, this if I see, I draw the midpoint around that, I will see that there is a curved profile. So, it is like, I mean, I have taken this other earlier airfoil and bent it slightly or curved it slightly. So, this kind of shape is called a cambered airfoil. So, we have symmetric airfoils and cambered airfoils. They both have slightly different behavior, which we will also talk about. So, what happens now when the airflow is going over this kind of airfoil, be it symmetric or cambered, as long as it is at some angle which it makes with respect to my horizontal. So, if I again draw the chord line and look at the angle it makes from the horizontal, okay, assuming my flow is in this horizontal plane and in the same plane. So, the angle made with this direction and the chord line is normally called, denoted by an angle alpha, and we call it as angle of incidence or angle of attack. So, what do we call? We call it as right. So, this particular airfoil, when I orient it at a certain angle with respect to the oncoming flow, it will generate what is called as lift force, and that is what I mean keeps your aerial vehicle airborne. So, how does this lift force come? What is the source of that? And the answer to that is actually this pressure distribution over the airfoil. So, you see on the top and the bottom surface there is always some amount of suction, and more so on the top surface compared to the bottom surface. So, this is how the pressure is distributed, and if I integrate this entire pressure distribution over the top and the bottom surface, I will be able to get the net resultant force, which we will probably see in the next slide. And beyond this pressure distribution, there is also some amount of skin friction on the body of the airfoil, right. So, when you walk or when you drag something on the surface of the ground, you experience friction force. So, similar kind of friction force is there between fluid, which is air in this case, and my airfoil surfaces. So, the fluid which is in contact with the airfoil surface will actually stick to it, which means it will go to 0 velocity, and it actually results in something called a boundary layer and all, which we will not cover in this class. If those of you who are getting a chance to do aerodynamics 1, you will probably talk about that in that class, but it is not very critical. To design a UAV, I do not have to worry about boundary layers right now. Okay. So, nevertheless, so and that sticking part actually will create this shear force. So, there will be some skin friction drag. Okay. So, the pressure distribution will create lift and drag, and it will also create some skin friction drag also. Okay. So, this is an additional component of drag. So, I will come back to that video again, but before that, I mean, what we discussed, let us just look at that. So, this is a more exaggerated view of how the pressure would look like actually. Now, question is, how do you get this kind of pressure profile? If I really want to know this, how do I measure this? Any idea? Well, what we do actually in our aerodynamics laboratories is that we will make this airfoil section and put pressure taps inside all along the chord line, okay, or sorry, all along the top surface, all along the bottom surface at some small distances, and finally take the output from that and put it in some transducer, which will be able to measure all this. So, if you do that, you will get this kind of top pressure distribution, bottom pressure distribution, and if I integrate all that, I will finally end up getting this purple line, which is my total pressure force, okay, right. So, this is my total pressure force, which I can then resolve about vertical and horizontal components. So, the vertical component is my lift force, okay, what is lifting it up, right, okay, and the horizontal component, which is in the direction of the flow. So, you see, this is the direction of the flow. So, in this direction, whatever force is there, that is called the drag force, and this is the force I have to overcome to make my UAV fly forward. Right. So, my aerial vehicle will fly forward if I am able to balance this, right. So, this is just like I mean opposing friction to move forward if I am trying to drag something. And if you want to plot this as a non-dimensional pressure coefficient, the graph looks like this. So, this is for the top and this is for, so this is for the top surface, this is for the bottom surface, okay. And the convention is that see top surface has negative pressure. So, that is what actually you put as a top. So, this is like a inverted way of plotting the graph. So, you see the negative sign is on the top. So, this is the suction which actually gives you enough force. So, this pressure multiplied with this overall area would give you force, which turns out to be my lift force, fine. So, now we will go a step backwards and look at this video, which will tell you why exactly this pressure distribution is there at the first place and how do we end up getting lift and what happens to an airfoil if I keep increasing my angle of attack forever, because different angles of attack will give me different amount of lift. Lower angles will give me lower lift, higher angles will give me higher lift, but only up to a point. So, let us play this video. So, this actually I have taken from YouTube. So, it is not really my own original creation. So, this is a very nice video where I mean they have put this airfoil in a smoke tunnel. So, what is a smoke tunnel? It is a regular wind tunnel, basically an area where I mean I can have a controlled nice laminar flow happening, and in that area I actually can insert some smoke which allows me to visualize the flow. So, you can see very nicely what we saw as the streamline. So, here you can now visualize the streamlines. So, they are not really imaginary things, they actually represent what really happens. So, I mean it is not like I have to draw a line somewhere, okay. I mean there are infinite lines, every point actually would trace a line. So, I will not draw infinite lines, I will draw some lines. So, same way I mean I have inserted some streaks of smoke which is going over the flow and giving you a nice feel of how things are. So, here we have put, so a lifting airfoil means I mean my airfoil is at such an angle of attack that it is generating some lift. A symmetric airfoil when put at 0 angle of attack will generate 0 lift, because top and bottom will be exactly symmetric, same kind of flow. So, pressure distribution on top and bottom would cancel and you would not get any lift.
We do the same test in our wind tunnel facility as well, sir.
Right. No, so I mean, yeah, you can go and do. I mean, so we have a lot of wind tunnels where you can easily go and do. So, but yeah, this is normally I mean UG experiments that do this kind of thing. So, as part of our course curriculum, you will not get this normal opportunity. But yes, if you end up designing something or working on some problem where you are investigating flow over wing or whatever, then I mean there is an opportunity. So, even most UAV designers, to verify their design, they will actually bring it down to our National Wind Tunnel Facility and they will insert the model. For example, ADE, DRDO Lab, Aeronautical Development Establishment, they have been working on male HALE class UAVs. So, they had brought the scaled version of their UAVs and put it inside the wind tunnel and sort of tried to measure the performance of the scaled down model. Okay. So, there are tricks by which you can measure that, okay, and get fair information regarding full scale model. So, you do not have to make the whole UAV and stick it inside the tunnel. That also can be done actually if you have access to such tunnels which are very expensive to operate, yeah, because it consumes huge amount of energy. Okay, now coming back to our smoke tunnel experiment. So, here you see nice streamlines flowing all over, but when we pulse this thing, okay, which means I mean I will sort of block the flow of smoke intermittently. So, you will see pulses of smoke going, and this will give you some very interesting insight. Okay, so, they will now slow it down, okay, and then you will see something very interesting. So, you see, pause it at the wrong point, yeah, right here. So, you see this is more or less a uniform smoke front, okay, which tells me that they are all coming at a same velocity more or less. Okay. But the moment they hit the airfoil section, you will see that the smoke particles or the flow over the top would actually accelerate and become faster. So, the flow on the top part would actually come out ahead of the flow on the bottom part. Okay. Let us see. You see it has now already touched, right. So, it is already going over the airfoil now and it is already going ahead. So, if we let the video play, you see in no time it has sort of raced ahead. So, here we can clearly see that the top surface has seen the flow accelerate and reach higher speeds and go faster, and therefore, they are leaving the airfoil. So, this is the trailing edge, you can see they have come out of the flow or come over the or crossed over the airfoil ahead of what the flow which was at the bottom side. The question is why? And actually this acceleration and deceleration. Okay. So, this will probably take us to very basic concepts of your Bernoulli's equation, for example. Are you familiar with Bernoulli's equation, all of you? Okay. So, how does it look like, Bernoulli's equation? So, P, right, plus, right. So, some V square rho V, half rho V square kind of term will be there, right. Okay. Plus, if there is height change, I mean there will be some potential energy term also, right. Okay. So, some mgh kind of term will be there, right, okay, equal to constant, right. Okay. So, here I mean my heights are not changing, so the mgh term does not play any role, but my pressure and velocity. Okay. So, my pressure term and the kinetic energy term, okay, they are going to change, okay, and that is what happens here. So, this also sort of relates to, so this is conservation of energy equation, then we have conservation of mass equation also, right, which means my m into A, which is a mass flowing through a cross section A. Okay. So, if I denote a area, okay, some area, it could be tube, rectangular, circular, does not matter. So, mass flowing through that would remain constant because there is no mass creation and there is no mass addition happening. So, if there is some flow happening in a conduit, my m into A, that is my total mass has to remain conserved, which means if I change the area of cross section, my mass flow rate is going to change. And what is, so this is not just m, it is actually m dot rather. Okay. So, this m dot is going to change, and m dot actually has your density term, your velocity term, etc., right. Okay. So, something similar is happening here, which means I mean the moment I look at my airfoil like this, the airfoil has a curved surface. Okay. So, this curved surface, the moment flows starts going up, if you see this actually acts like a converging nozzle kind of thing. Okay. So, if you imagine a scenario where I mean you have a tube and water is flowing through that and you try to choke the thing, your water speed will immediately go up, right. Okay. So, that is what is happening here, because of this curved surface of the leading edge of the airfoil, the flow actually has to go, it actually sees a kind of pressure gradient which tries to accelerate it, the way it will be as if it is going through a funnel, right. So, that is what I mean is making it accelerate on the top, and at the bottom it is a fairly flat thing, okay. It is a fairly nice flat smooth area. So, flow I mean almost keeps going without a dramatic change in its speed. So, this is what actually accelerates the flow on the top, while the bottom flow goes at a normal pace more or less, and this ends up creating this suction. Okay. So, that is what I mean changes my static pressure on the top surface and creates a suction which in turn creates my lift force, which tries to lift my airfoil up. Okay. So, we can continue looking at this video. So, now the second part of the experiment tries to talk about what happens when my airfoil angle of attack is changed to a larger value. So, you see now there is some angle of attack. So, there is clear pattern, and then once I start increasing my angle of attack further and further. So, if I go back a little bit and see the difference. Okay. So, right. So, you see here till moderate values of angle of attack like 6, 7, 8, 9, 10 degrees kind of thing, my flow is going nicely over the airfoil, means it is leaving smoothly from here, from the trailing edge. Okay. So, the entire duration it is remaining attached to the surface of the airfoil, but the moment I go to higher angles of attack, it will no longer remain attached. So, you see this point you will see this will start lifting up, yeah. This is called flow separation. So, the flow is now separated from the airfoil surface, and this creates a huge wake structure. You see this is vertical things which are happening here, okay. There is the circulating flow happening here. So, this area does not seem very nice, and this actually is called stalling of the airfoil. Okay. So, what does this mean? Means that I mean the lifting capacity will now drop. whatever lift was there, it will now come down. It may come down to much smaller value or less value depending on the nature and design of the airfoil, but you will definitely see a decrease, and decrease in lift and increase in drag, because the pressure profile here will be more arbitrary, not nicely done. And question is, why this stalls or why this flow separation happens? Sort of, yes. So, the what happens that now when I have angle this airfoil at a low or moderate angle of attacks, we said that my flow will accelerate here. Yeah. But now, so initially it is actually my surface is like this, so it actually has to sort of climb up here and it will accelerate, but then it is downhill from here, right. So, if you see now I am actually making the flow go through a very diverging kind of section, because my airfoil is like this, right. So, my airfoil surface is here, and you can imagine the flow which is coming, it actually now has to expand in some manner. Okay. So, imagine it is going like some amount of flow is there, I am suddenly making the cross section wider, which means I do not have enough mass to fill all this area, right. So, my mass flow rate and the speed associated with that actually will drop dramatically. So, this creates sort of a adverse pressure gradient, which means now the flow is facing some resistance to remain attached to the airfoil surface, okay, and that would actually cause it to separate. So, it is like resistance that this pressure gradient is creating, which causes the flow to separate and further results in stall. Yeah. So, you see this creates a lot of vertical flow.
So, the creation of this vacuum is a bad thing for us in aerodynamics.
Yeah, it is actually. So, it is not really vacuum, okay. There is flow, but there is circulating flow, it is not a proper coherent flow. There will be a lot of eddies and so you if you move your hand inside a bucket or a water source, you will see these small whirlpools going around, right. So, those are your vortices basically. So, it will have this kind of vertical flow in that area. So, your pressure will be arbitrary and it will not create suction anymore, and that is why your drops. So, we will be able to visualize that further by looking at some of these diagrams, where you can see how my increase in angle of attack creates a pressure gradient, which eventually causes the flow to separate. Okay. So, this is again taken from internet. So, here we see I have an airfoil and look at the relative airstream. So, this is actually a cambered airfoil. So, we can see clearly that there is a pattern on the top surface which creates a nice suction pressure on top. So, my center of pressure would come out to be somewhere here, and if you see here my pressure is building up and then after that pressure is going down. Okay. So, you can see if I take a derivative of pressure at any point, it will tend to become negative, right. So, it is decreasing pressure, increasing pressure, decreasing pressure on the profile. When I go to a moderate angle of attack like 6 degrees, okay, so it is a moderate angle, you see this entire profile of pressure, this negative pressure pattern actually tilts forward. So, it moves slightly forward again, because see the profile is such that initially you see it has lesser, here there is I would say greater increment in the initial pressure development, okay. And later on it is, so if you see it is all because of the nature of the surface. At lower angles of attack, your initial convergence versus further divergence is all gradual. Later on once I keep inclining it more and more, my initial suction creation will be higher, but later on there is much wider gap now. Okay. So, the flow in this area gets more diffused, right. So, it is actually seeing higher pressure gradient, and therefore, it will tend to, so my lift actually shifts slightly forward, okay. The area of more suction shifts forward. Okay. So, right now see we are not talking about boundary here, we are talking about the pressure actually, okay, like how the pressure on the surface actually is being experienced. And when you go to even further higher angle of attack, my center of pressure also moves quite forward, you see. So, my center of pressure is here, it is slowly moving forward, it moves even further a bit more, and my overall pressure resultant also shifts quite forward. And so, this is around when you will start experiencing stall. So, you see at the later part of the thing, my flow is now actually almost separating, it is not actually going along the trailing edge as it was in the previous case. So, you see it is going nicely from the trailing edge, here also it was still going close to the trailing edge, but later on it is now no longer going all the way to the trailing edge, okay. Because at higher angles of attack this area sees more significant negative pressure gradient, which sort of pushes the flow away, okay. And when you go to even further higher angle of attack like 18 degrees, where I mean almost every airfoil will be stalled, you see my flow separates right from here, okay. Very early stage it will separate, because going down here is not possible, because there is too much of area to cover and very high pressure gradients to cover. So, it will separate very early and the wing is stalled. So, you see now the top surface suction is minimal.
Positive pressure underneath, it should be pushing the.
Yeah, it is there, but this is still going to be less than the suction. So, you will have now more drag. So, many airfoils you will see that after stall it will not really go down to 0. It will have a dip and then it will sustain the lift, but that lift comes at a very high cost of high drag. Okay. So, that is how it actually happens. So, we will look at those lift curves to understand this better at a later stage. Okay. So, now so earlier we talked about, I mean, your quantities like density, we talked about fluid velocity. We will now bring another parameter called viscosity of fluid. I mean, you may have learnt about this in your school. So, by using these parameters we can actually define a very important non-dimensional parameter called Reynolds number. This actually has significant bearing on the aerodynamics of any aerial vehicle, because it directly relates to the scale. So, if I am making a big UAV versus a small UAV, my aerodynamic behavior will be significantly different, and that is dictated by this particular non-dimensional parameter called Reynolds number. So, let us understand this in better way. So, what is this? So, it is denoted with this symbol Re. So, it is the ratio of inertial forces to the viscous forces. What does it mean actually? Let us try to understand that. Within a fluid which is subjected to relative internal movement due to different fluid velocities. So, Reynolds number for let us say aircraft wing would be defined by using rho v, and the reference length will be the chord length of the airfoil. So, what is the chord length? So, we take this airfoil and that line which we drew, right. So, this line, so we drew this chord line, right. So, this distance is my chord length. Okay. So, any airfoil if I draw this straight line connecting the leading edge and the trailing edge, the total length of this line is my chord length. So, this actually ends up becoming my reference length when I define my Reynolds number. So, always we will do that only, okay. We will not change that. So, now if I take a smaller UAV, maybe weighing say 5-6 kilograms, okay, with a span maybe 1 meter, okay, or 1.2 meters, the chord length could be probably 10 centimeters. So, my 10 centimeter chord length will be the reference length in calculating my Reynolds number. And if I compare that with a larger UAV, okay, a male class UAV, Searcher, Heron, Bayraktar TB2. So, all those drones actually have much larger wingspan and chords would be probably in the order of meter probably. So, you can understand my Reynolds number, and yes, of course, the velocity will be also different, right. So, the smaller UAV will typically fly at 20 meter per second, maybe 15 meter per second, while my larger UAV would operate at speeds as high as 100 meter per second, if not more. So, 100 meter per second would mean 360 kilometers per hour, right. Okay. So, that is also pretty high for a propeller driven UAV typically. Okay. So, but let us say, I mean, if it is 100 meter per second, here we are talking about 20 versus 5. So, there is a factor of 5 involved, and similarly for my chord there is almost a factor of 10 involved. So, you can understand my density remaining same, my air viscosity remaining same, my Reynolds number will be different by an order of 50 at least, if not more, which means my larger craft has higher Reynolds number, while my smaller crafts will experience lower Reynolds number. But how does that affect? What is the impact of that? Sorry? Well, so the definition of Reynolds number itself will tell you the answer to that. Okay. So, just read the definition again for yourself. Ratio of inertial force to the viscous force. What is the viscous force? We talked about, I mean, fluid sticking onto the airfoil surface, right. So, that is because of viscosity. If the fluid was not viscous at all, it would not stick to the surface. And if my Reynolds number is higher, which means that there is lot of energy in the flow, there is lot of kinetic energy in the flow. So, my inertial forces are more dominant and they will overpower the viscous forces. So, the drag and all will not have a more critical role to play. Okay. So, I will not let that stick too much, okay. I mean in a very layman's manner actually, I am not trying to give you very technical explanation for this. While if I go to a lower Reynolds number, my viscous forces will now start to dominate. Okay. So, my flow will stick more to the airfoil, which means it will create higher drag, lesser lift. So, my higher Reynolds number, my lift would be more, drag will be less. So, my L by D would be on a better side, on a higher side. So, I am talking about L by D. So, my lift to drag. Yeah. So, this is higher if my Reynolds number is higher, but what is high? So, as an engineer it is very important to have a feel for numbers. If you do not have feel for numbers, then I mean you will not understand, I mean if you are going right or wrong in a design process or in a calculation process or anything. So, Reynolds number for full scale aerial vehicles is of the order of a million, 10 to the power 6. For full scale is of order of 10 to the power 6. It is a non-dimensional quantity, remember that, right. It is a non-dimensional, so that does not have any units, it is just a number. So, that is the order it has actually. And if I go to a smaller scale, like I talked about the DARPA's challenge to make a micro aerial vehicle, right, where we had to make a small UAV which would be less than 10 centimeter in any dimension and fly for 1 hour, 60 minutes of flight time, right. So, those kind of scale UAVs which were really tiny UAVs, micro aerial vehicles as they used to be called, they would experience Reynolds number of the order of 50,000 to 100,000 maybe. And if I talk about 5-6 kg UAVs which are small UAVs which could be hand launched or catapult launch or something, they may have Reynolds number of the order of hundreds of thousand. Okay. So, for small UAVs, can range like 10 power 4 to I mean 10 power 5, something in 10 power 5 basically. So, 100,000, 500,000, 300,000 depending on the scale again, okay, and the speed that it is operating at. Okay. And the direct bearing of this Reynolds number is on your lift to drag ratio. So, you cannot expect to have a performance of a large UAV or full scale UAV on the smaller scale UAV, because you will not be able to match the same lift to drag ratio. Lift to drag ratio will be directly governed by Reynolds number. And I do not know if I mentioned this Ingenuity helicopter which flew on Mars, right. It is a UAV, first UAV or first aerial vehicle to fly on a different planet. It was sent by NASA to Mars, and it was accompanied by Perseverance rover, and this Ingenuity helicopter was dropped on the Mars surface and it flew there. So, the Reynolds number that this particular UAV was experiencing there was the order of 10,000 to 20,000. Okay. So, this Reynolds number itself actually made this flight possible. If it was lower than that, then it would have not have been happened. So, even on Earth, if I make a really tiny aerial vehicle, okay, my Reynolds number will be of the similar kind. Recently, you may have seen this news from Chinese scientists making some really tiny mosquito size something flapping wing thing. It is actually a copy of work done at Cambridge 6 years back. Okay. So, Cambridge University, they had already built this kind of thing. If you look at that picture closely, you will see that that particular tiny flapping thing is connected through a small wire, okay, which gives the power supply. So, it has a tether attached to it. So, it can only flap here on your table, it cannot go anywhere else actually. So, this was built, it is a good scientific work, but we do not have to worry about some mosquito flying inside and taking our video anytime real soon, okay, because there is no such power source for such tiny things. And the Reynolds number for that kind of tiny things. Okay. So, if I look at your insects, bees, fruit flies, they all operate at Reynolds number of the similar order 10,000, 6,000, 12,000 and like that. Okay. So, there actually this unsteady aerodynamics and flapping movement and all actually gives you certain advantage. Okay. So, again I am going too deep into aerodynamics. So, we will not go there, right, but that should give you a sense. Smaller crafts have lower Reynolds number, larger Kratz have higher Reynolds number. Higher Reynolds number is better, it enhances my L by D. Lower Reynolds number has higher viscous effects, so my drag becomes more and lift drops. Okay.
So do we have a threshold Reynolds number, or like after this Reynolds number only we can fly?
No, everything will fly, okay. But you will have to pay the price for that. Okay. So, if you are operating at low Reynolds number, you have to pay the price, and you have to actually choose design choices or make design choices which are better for low Reynolds number. Okay. So, this is something which people learn, that I will give you one sort of a heads up before we really go and discuss that. At low Reynolds number, having thickness in my airfoil is a bad thing. I do not want to use thick airfoils or airfoils which actually look like airfoils. I am better off using flat plates, okay, or curved flat plates, means flat plate with some camber, instead of using a regular airfoil which has thickness. Okay. So these are the kind of choices one has to make when you operate a certain Reynolds number, to take advantage of the unique features which are there. So, people have done this kind of fundamental studies to see what works well at low Reynolds number. Okay. Now, other important parameter which would probably not bother us a lot is Mach number. Okay. So, what is this Mach number? It is a ratio of my craft velocity, which is same as fluid velocity, right. So, I can look at two different approaches. Again, there is a Lagrangian approach and things like that. Okay. So, we will not go there right now. The point I am trying to make is that if I have this airfoil, right, it is either translating in air, or I can think airfoil is stationary and flow is going over that, right. So, it is one and the same thing, it is just relative velocity idea. So, when I say fluid speed is so much, which means my craft speed is the same, assuming it is flying in a stationary air, right, there is no wind or something like that. Okay. So, either I look at the flow velocity, which is V, which I call free stream velocity, or it is my craft velocity. So, V divided by speed of sound is my Mach number. So, this actually becomes more relevant or critical when you start operating at higher and higher speed, and which is actually happening, because recently in the ongoing Russia-Ukraine war, Russia launched certain new upgrade version of these Shahed drones, which were powered by jet engines. So, they would fly at very high speeds as high as 600 km per hour, which means it is almost double the speed of normal propeller driven Shaheds. Okay. So, propeller driven Shaheds will actually go at 250-300 km per hour max, okay. And now these jet driven ones are actually going at 600 km per hour. So, 600 km per hour is how many meters per second? Can anybody calculate and tell me? You have phone, calculator, or I can do it myself. Yeah. So, 600 divided by 3.6 is 170 meter per second, okay, right. And what is my speed of sound? Typically, you take 330 meter per second, okay, the normal condition. So, divided by 330, which means you are operating at 0.5 Mach number, that is what we are defining here. Okay. So, normally if anything is moving faster than 0.3 Mach number, you would have to be concerned or aware of the compressibility effects. Okay. So, that actually starts playing a role. So, your aerodynamic has to have certain corrections to account for all these things. If you are only working with propeller driven things, then we are at low subsonic speeds, we will barely touch 0.3 Mach number, and in that case we are fine. But if I am operating a rotary wing system, where my rotors are large and we are operating at higher RPMs and so on, then again my rotor may actually start coming close to 0.7, 0.8 Mach number actually, if I try to fly faster. And that is one of the constraints why helicopters cannot fly faster like an airplane. If the top speed for a manned helicopter is how much? Typically 150 knots, okay. So, which means 300 km per hour, give or take a little bit here and there. Okay. So, 300 km per hour is nothing compared to a commercial airplane flying at 950 km per hour, right. So, why does helicopter not fly? Because of the same problem. Okay. The tip of the blade will start seeing Mach number going beyond 0.8. And these manned helicopters, they in hover condition itself, when they are not even flying forward, the tip Mach number is already close to 0.6 for full scale versions. Now, smaller ones may not go all the way there, but still they will have 0.3, 0.35 or their kind of Mach number easily coming there. So, that is where this Mach number plays an important role. Now, what happens if I go to a higher Mach number? I said compressibility effects comes into picture. What is compressibility? My flow, air flow, air is a very compressible medium. So, if you look at fluid as water, it is highly incompressible. So, people do not have to worry there about this compressibility, but air, the moment I go to higher Mach numbers, the flow behaves in a certain manner that if I go close to say Mach number 1, when I have the same speed as the speed of sound, or if I go to a higher speeds than sound, then a phenomena called shock waves start to get generated. And in a very layman's manner, why it is called shock wave? A boom, yes, but why is shock? Who is getting shocked here? The fluid actually gets a shock. How?
Normal fluids travel at the speed of sound.
Yes. So, not normal flow, but see, every time you create a disturbance in flow, your disturbance information inside the flow propagates as a longitudinal wave at the speed of sound, right. So, which means aircraft or my UAV moves through the air, the particles ahead of this point, they will get to know that something is coming my way through this sound wave travel. Okay. So, this information or this kind of disturbance information will travel in the media at the speed of sound. Okay. But now, if my disturbance creating object, my UAV or my aerial vehicle itself is moving at speeds more than sound speed. So, now before this information reaches them, my UAV has reached there actually. So, they are literally shocked that, and hence the name shock, okay, shock wave, right. So, these things actually will come into being when I operate above 0.8 Mach number, that you can start experiencing shocks, and that also results in something which is called drag divergence. So, we just talked about drag force. So, if I sort of make a plot of this drag force D as a function of Mach number, okay, you would find that it would experience a dramatic rise beyond say 0.8. Okay. So, your drag would shoot up and increase to very high numbers, and that is why operating supersonic aerial vehicles is very expensive and highly fuel consuming. And that is why your Concorde airplane, world's first and last till date supersonic airplane, could not be sustained, because even though government was subsidizing the ticket and everything, it was more of a luxury and more of a curiosity. Nobody would really use it for regular travel, even though Concorde was a real engineering marvel. Some exciting engineering went into designing it actually, okay, right. So, but anyway, but defense forces can always afford supersonic things, okay, because there you are not worried about saving your money, you are just worried about saving the country and hitting out at your enemy. So, but in general sense, we will not really try to design a supersonic UAV just like that, okay, because it more so goes in the realm of a missile than actually a UAV when you go to such high speeds. All right. So, this now brings us to point where we now take a look at the anatomy of a fixed wing aerial vehicle. So, my UAV would be exactly like this, although this is a picture of a manned aircraft. Again, I have taken this image from internet, okay, just to highlight what are the key parts of a aerial vehicle. The key difference between this image and UAV, so maybe next class I will bring down a fixed wing UAV model from our lab, you will get a chance to look at that, is that this actually has a cockpit where a person can sit. A normal UAV will not have that, and sometimes and a lot of UAVs have been built by using your manned aerial vehicles and converting them into unmanned. Okay. Like I mentioned that F-16s are now no longer fit for, many old F-16s are no longer fit for a human pilot to fly it, but autopilot can always make it flyable. So, that is the idea. So, same craft I can convert into what is called an optionally pilotable aerial vehicle also. But if I compare with a fixed wing UAV, it is exactly how it would look like, which means I would have a propeller which would give me forward propulsion. I have a wing which is supporting my weight, giving me the lift. I have a horizontal and a vertical tail which enhances my stability and also provides some amount of control. And I have a landing gear which will allow me to do a ground run and take off. Most smaller UAVs will not have a landing gear, especially if I am making something which I do not want it to come back, kamikaze kind of role. I will not put a landing gear at all because it is not supposed to land. I will somehow throw it, launch it by using some catapult, some jet assist or whatever, and not worry about landing gear, because the moment I put a landing gear which is not retracting, it will create drag, right. So, I do not want to have that actually, and it also adds weight. So, landing gear, but yes, if you look at a male HALE UAV, it will have a landing gear also. Then I mean we have these colored things marked out which are what we call as control surfaces, and this is what actually you would actuate or work with to manipulate my motion of the aerial vehicle. So, we have these green things at the end of the wing tip, it is called ailerons, and what do? We deflect them in a asymmetric manner. So, if I deflect one down, other will go up. If I bring this down, this will go up, which means I actually want to use it to increase the lift on one side of the wing and decrease the lift on the other side of the wing. But how so? So, if I look at the, so this actually can be thought of as a, if I draw a normal airfoil, and this aileron could be thought of as a small flap which is embedded inside this airfoil and which can be deflected up and down. So, if I deflect it down, it actually increases my camber, basically my curvature is increased. If I increase the curvature, my airfoil will generate more lift for same angle of attack. So, that is what we do. If I deflect this down, I will have more lift. If I deflect this up, I will have less lift, which means this side with more lift will try to go up, the other side with less lift will try to go down, which means my airplane will try to roll. So, we have three motions, right. I mean we have this. So, for every aerial vehicle we have these three motions. So, about this axis any rotation is called rolling motion, about axis maybe in this direction any rotation is called the pitch motion, which means my craft, if this is my craft, this motion is my pitch motion, this motion is my roll motion and this motion is my yaw motion. So, which I will define another axis here and this would be my yaw, right. So, I can see that if I deflect these things I can make the craft roll, but why I want to roll it like this? Because that is how I actually want my aircraft to turn. So, this is one of the very early things which the inventors of airplane, Wright brothers actually figured out long before they did their first flight. They realized that it is not very good or nice to turn the aircraft by simply deflecting my rudder. You see this red thing? So, this is also a vertical wing which actually has the same flap, which if I deflect it will create a force, and this tail force in the horizontal plane rather would create a moment about this, about the yaw axis. So, this would try to turn it, but that kind of turning is called skid to turn, and in airplanes we do not do skid to turn, it actually causes side slip. So, even for a manned aerial vehicle it will not be comfortable because you are, it is like slipping, so you are trying to turn on a road and you slip, so you are skidding out actually. So, this actually is neither very comfortable for a pilot or a passenger to be sitting there, and it is also challenging from controls point of view for such kind of large aerial vehicles. So, you do not do skid to turn, you actually do bank to turn. So, I bank on one side and with that I can actually rotate and turn. How? The moment I bank, a component of my vertical lift force would tilt and give me centripetal acceleration to allow me to go in a circular path. So, it creates a centripetal force. So, you see the moment I turn this direction my lift vector will turn like this. So, I have now a horizontal component of lift which would allow me to. So, it is just like, I mean you tie a mass to a string and spin it, right. So, it goes in a circular path and the tension in the string is providing you that centripetal acceleration. centripetal acceleration which is keeping it flying in a circular path. So, same thing happens to my airplane also. So, that is how my airplane can now bank and turn. So, this green thing ailerons are responsible for roll control. Okay. What about the blue thing, my elevator? So, that will actually give me the pitch control. So, if I deflect it downwards, it will increase the lift on the tail, which will make me go nose down. Okay. So, it will, if I want to descend, I can descend with this. If I want to go upwards, I will deflect the elevator upwards, which will decrease my camber. So, decrease the lift on the tail, and thereby tail will drop down and my aircraft will tend to climb. Okay. So, it is reverse, means the direction in which you deflect, that is the direction in which my aircraft flies. If I deflect it upwards, aircraft will try to go upwards. If I deflect downwards, airplane will try to go downwards, like that. Okay. So, this is for pitch control, and so this is for ailerons are for my roll control. And so what is the role of rudder then after all? Because I am, no, but what yaw? I am yawing by turning actually, by using my ailerons.
Supplement to turning with ailerons.
By doing what?
I mean, by controlling the rudder with the help of ailerons, it will act as a supplement to the ailerons for turning.
So, what happens, I mean, when you start turning, okay, and the moment you bank, you will start to turn. But at that point of time, I mean, if there is any disturbance or any such thing, say if there is a crosswind, or even when you turn, I mean, you will actually generate a sort of a your tangential speed also, right, because you are rotating, right. So, you have now a component which is in the direction perpendicular to your aircraft motion, right. So, this actually creates a side flow, which will try to sort of create some kind of side slip for your aerial vehicle. So, your aircraft may try to side slip, which means, see, normally if I fly, I will fly like this, but I may end up flying like this, right, you understand, which means, I mean, my tail will be slightly wagged. So, this rudder helps you correct those things. Also, if I am trying to land straight in a crosswind scenario, okay, so my aerial vehicle is coming like this, but there is wind from this side. So, what happens the moment the wind is from this side, I mean, airplane will try to, due to its own natural longitudinal stability, it will try to turn into the wind. So, you have to cancel that. You do not want to, your runway is like this and you cannot land like this, right. Okay. It is not very comfortable. So, to ensure that I can maintain it like this, I can cancel that tendency by using a rudder. So, rudder is used to mostly correct side slip. So, side slip is what? Side slip is basically sort of a, so my aircraft has this angle of attack with the horizontal airflow. If I have a sideways airflow, that creates a different angle. So, this angle is called side slip angle basically. So, in plane airflow will create this side slip, which I cancel using rudder. Okay. So, I mean, what I am trying to say is that if this is my airplane, so you may end up getting a velocity component like this. Okay. Yeah. So, this angle would be your side slip angle, and I can actually correct that by using my rudder here. Okay. Yeah.
So when we are banking to turn, we have a centripetal force acting on it.
Centripetal acceleration.
Yes.
Centripetal is not a force. The pseudo force to sort of define centripetal acceleration is called centrifugal force. Yeah.
So where could we place the axis for it, sir? Like around which does the plane turn?
No, so that is, I mean, depending on, I mean, by what angle you are banking, right. So how much you are banking by?
Will the axis be on the aeroplane or outside?
No, of course outside. So it's not rotating on its own. See, it's not rotating about its own CG. The rolling, pitching, yawing is all about the body axis, but your overall rotation, the turning, is about some point far away. So, that will be called your turn radius. So, turn radius will depend on at what speed you are at and how much you are banking. So, based on that you can decide your turn radius. Yeah. Of course, it will be also because you are trying to execute a big circle. Okay. Right. So, you want to fly in a circle. So, you define a center of the circle and a radius. So, even in UAVs when you plan their trajectories, so fixed wing UAVs, right. So, if I wanted to go to a target and then loiter. So, in loiter I mean in all autopilot modes you will define a loiter point, radius around that. So, it will now set a center of the circle and then it will go on a execute a circle around that center basically with the given radius. Okay, so, that is your loiter. So, it will keep flying in that circuit forever if you have that much of energy left, okay, or you do not command it to go elsewhere. Okay. So, that is what it does. So, it is always outside airplane. For as UAV it will be way far, I may be flying in a circle of 100 meter radius, 200 meter radius. Okay. So, okay, so that I hope gives you fair idea about how I control a fixed wing aerial vehicle. Okay. Now, beyond that model I have also put some additional things here, again taken from internet. So, beyond whatever you saw in the previous picture, now we have some additional things, these flap things are there, right. Yeah. These are not there normally in small aircrafts and also UAVs. They are typically there on slightly bigger aerial vehicles. What are these and what do they get used for? Yes, they are called high lift devices and they are used primarily to reduce your takeoff and landing speeds. Sorry?
As brakes.
Brake is a different thing. Okay. So, they may also they do not get directly used as brakes, there are separate things which are called brakes. So, if I go to the next picture you will be able to see everything. So, this is actually a nice commercial airplane, again the image taken from internet. So, here you will see many extra things now. So, you will see in the front there are slats which actually come out of the wing and you have now this whole red thing here is that extra flap. They are called takeoff and landing flaps because they will get deployed only for the time of takeoff and landing. So, what happens is that now a commercial airplane typically flies at almost 900 km per hour or thereabout. My takeoff and landing speed is barely 250 to 300 km per hour. So, the gap of 1/3. So, I cannot take off and land at 900 km per hour, that is obvious, because that would require enormous engine power, you have friction and so many things on the ground. So, how do I make my airplane become airborne at much lower speeds? So, for that these extra devices are there. So, we deflect this flap downwards which increases your camber. These slats they come outside of the wing and they sort of increase the chord of the wing. So, my wing, so if this is my airfoil, it will actually get expanded somewhat like this, with flaps getting deflected and some things coming out here. So, this are embedded inside and they will come out and expand the chord length. So, now with a increased chord and higher camber, I can generate more lift at the lower speeds. So, that way I can take off and land at lower speeds, and once I am airborne, I will retract these. Question is, why do not I fly with this all these extra lift devices always in position? Right, exactly. So, nothing comes for free. If you get more lift, it will come with more drag. So, L by D is not very good for this, because of that I will want to retract everything and have a more cleaner and leaner design where my L by D is optimal, and then I will be cruising at higher speeds but in a more optimal manner. But typically in a UAV you will not find any of these extra things, because it will add to a lot of complexity and we will not have room to put so many things. Even male HAL UAVs, they may have some surfaces, additional surfaces, but I would not expect them to have slats. They may have takeoff landing flaps if you wanted to do some stall or some such thing, if I want them to operate from say ship decks if needed. Even though on ship decks normally you will have some catapult kind of thing which will quickly accelerate it over a short distance to make it airborne. But yeah, normally all these extra things are not there, but just for your information, on a commercial airplane all these things are there to enhance your lift and reduce your takeoff and landing speeds. Okay. All right. So, any questions so far?
Regarding that Reynolds number, so does it have any connection with the turbulent?
Reynolds number.
Yeah, the Reynolds number that we mentioned. So does it have any connection with the turbulent flow and laminar flow, the flow parameters?
Yeah, so in civil engineering they normally say okay, at a particular Reynolds number flow becomes turbulent and this and that actually. Okay. For I mean airflow point of view, I mean any flow can become turbulent and depending on surface condition and many other parameters actually. So here we do not really worry so much about laminar flow, turbulent flow. Okay. Yes, at very low Reynolds number, I mean the flow becomes creeping flow, okay. But that you will not observe with air. For that you have to use medium which is very viscous and so on. Okay. So like Reynolds number like 50, 100 and all that. Yeah. For us, I mean Reynolds number are fairly high, almost always our flow is turbulent. Okay. I mean at beyond a point, but yes, I mean we do make laminar flow assumption as long as I mean we are flying at lower speeds and not very high angles of attack and so on. So this flow is smooth, it is leaving the trailing edge nicely and so on and so forth. Yeah. So that is what we will use for simple calculations. But in reality, I mean in time everything actually has some degree of turbulence. So theoretical assumptions or modeling assumptions are not exactly same as what is actually there in the real world. Okay. So even a simple airfoil, if I try to do a simulation at different Reynolds number, you will see that I mean if I do a very high end time resolved calculation, say if I do a computational fluid dynamics CFD, you will see I mean some amount of perturbation and turbulence in everything. Okay. Yeah, so that actually brings a good point that whenever you build a new UAV and you are doing some flight test, you would always want to put tufts on them. What are tufts? Small pieces of threads. Okay. You would want to stick them over the entire surface of all the aerodynamic surfaces. Okay. So that when you fly, you put a camera and you will be able to see that I mean how these tufts behave in actual flight. Why? Because if the flow is nicely attached and everything, the tufts will remain attached to the body. The moment you see these tufts get elevated, there is flow separation happening, which means I mean you are incurring more drag in those areas and you need to work on fixing them in a proper manner. So this is a very simple trick which you must use if you design or build a new aerial vehicle, okay. And you are connecting flights to make sure that I mean there is no surprise, okay, that there is something which actually is disturbing the flow and some such things are happening. Okay. So if you use bluff bodies as any structural member, it will always create a lot of turbulence and a lot of separated flow, which can spoil flow on other aerodynamic surfaces also. So that is one challenge. I mean if we talked about this lift cruise type vehicles, actually VTOL vehicles, right. So VTOL vehicles I mean which has propellers in front of wings, they may create some turbulence which can create turbulent flow and it can actually compromise your L by D at certain points of time. Yeah. Alright, so we will stop here because time is up. So we will continue from here in the next class. Okay. By the way, Saturday is a working day, but we will not have our class on Saturday. We will compensate that class some other day. Okay, fine. So Saturday we are not meeting.